So now let's look at inverse functions. So inverse functions and exponentials and logs. Exponentials and logs, they are inverses of each other. If you take an exponential equation and you swap the position of y and x like I've done here and solve it so that it rearranges for y, you'll get a log equation. And if you take a log equation, swap your x and y, you'll get an exponential back. For circular functions, the inverse circular functions, so inverse sine, inverse cos and inverse tan, they actually require a restricted domain for the original circular function if they're going to exist. And if you're going to find inverse sine of something, whatever you're finding inverse sine of, you put in here. And just to show you that inverse sine is in fact the inverse of sine of x, if you find inverse sine and compose it with sine of x, you actually get x out. But I want to talk a little bit more about why inverse sine of x, when you use it on your calculator, only gives you one answer. So we all know that inverse sine of a half on our calculator will spit out one single answer and one single answer only. It spits out pi on 6. But we know from our work with the unit circle that there are many, many other sine values other than pi on 6 that have a sine value of a half. 5 pi on 6 is the next one round in the rotation. So let's have a look at what's going on and why your calculator, your scientific or your CAS calculator, will only give you one value when you use the inverse sine function. But when you solve, if you did solve sine of x is equal to a half for x, you get general solutions. Lots of it, lots and lots of solutions. Let's have a look why. So you can see the cos graph I have here and the fact that it fails the horizontal line test, and so it won't have an inverse function. But if I just take a chunk of that cos graph instead of the whole of the cos graph, and I'm going to take the cos graph for the domain of 0 to pi, I now have something that if I put the line y is equal to x, I can reflect that function across that line, and now I have the inverse cos function. And the inverse cos function is just has a domain of from -1 to 1. So this goes from -1 to 1. And so you can see that if I substitute any value in for inverse cos, say I put in inverse cos of a half, then I'm just getting one answer out for that. So here's our sine curve, and again the sine curve is not a one-to-one function, and so I'm going to take a section of the graph so that it can have an inverse function, so that it is one-to-one. I can't take 0 to pi like I did for cos because that doesn't give me a one-to-one function, but I can go from negative pi on 2 to pi on 2, and that not only gives me a one-to-one function but gives me all of the output values for sine of x. And so that gives me all of the possible input values I would be having for my inverse sine function. So again, if I put the line y is equal to x in and I reflect it across the line y equals x, you can see there that I have now got an inverse sine function. And again, the values for inverse sine, the domain of inverse sine is from -1 to 1. And that's why when you're finding inverse sine of a particular value, you'll get angles in the first quadrant, which are from 0 to pi, 0 to pi on 2, and also quadrant 4. So you'll get answers that are from 0 to negative pi on 2. Okay, so here's the graph of tan of x. Again, it's not a one-to-one function. So again, I'm just going to choose one section of the graph that is one-to-one so that I can have an inverse for it. So there's my line y equals x, and inverse tan looks like that. And so for our original restricted tan function, our domain was from negative pi on 2 to pi. And so for our inverse tan function, the maximum values it can have are from negative pi on 2 to pi on 2. And so that's why your answers, when you're finding inverse tan on your calculator, it will give you either an answer in the first quadrant or in the fourth quadrant. So let's have a look at the inverses of power functions. So what I've got here are all of the different shapes of, first of all, let's look at positive powers. So we've got our quadratic shape for our even powered whole numbers, our cubic shape for our odd powered whole numbers, so x cubed, x to the 5, our root shaped, our square root shaped graph for our power functions where the fraction has an even number in the denominator. We have our cube root shaped graph for our functions where the denominator and the numerator of the fraction in our power are both odd. We have this funny bird-shaped graph, which we get from having a fractional power where the denominator is odd, but the numerator is even, which means that we're going to find for this one the fifth root of x, and then we're going to raise that, whatever it is, to the power of 4. So all of our answers will be positive, and hence this bird shape. And again, your cubic function if your power is odd and odd. Oh, same one here and same one here. That's here to show you this little thing over here. Let's have a look at our negative powers. If we've got x raised to the power of a negative even number, we'll get the truncus. So this is like 1 over x squared, 1 over x to the power of 4. This is our hyperbola that we get for odd whole numbered powers. That should say 3. We also get one arm of a hyperbola or a truncus as the negative version of an even numbered root. So this is the equivalent of this, if you like. So we've got one branch of a graph and just one branch of a graph here. For our odd numbered powers, if we have those as negative values, you'll get odd values and even values. You'll get negative values and positive values, so we have a hyperbola as well. For our functions where our numerator is positive and our denominator is negative, which is different to what we've got here. Okay, this had an even denominator. This has an odd denominator but an even numerator. We get a truncus shape, and if we have odd numerator and odd denominator, pretty much like we had here, we get the hyperbola shape. So in terms of inverses for these functions, and these are all functions, we have difficulties finding inverse functions for the graphs which fail the horizontal line test. So any of these graphs fail the horizontal line test. So this one, this one, this one, and this one. And so if we're going to have inverses that are functions of these, these ones here, we need to restrict the domain. So let's look specifically at the new cases that we've just come across where you don't get an inverse function, you get an inverse that's not a function. And that is the case where the fractional power has a numerator that is even. Okay, so the numerator is even. So that's going to give us, if the fraction itself with the even number in the numerator is less than 1, between 0 and 1, you get this flapping bird shape. And if the fraction itself is greater than 1, you kind of get the bird with its wings up kind of shape, or a bit of a parabolic shape. And so the difficulty comes with recognizing that when you have at the top an even number, so think of this as being like x squared, then you've got the parabolic shape, and your inverse is going to have two arms. It won't be a function, and it will have two arms. And the reason that it works for this f of x is equal to x to the 4 on 5 is if you find the inverse by swapping your x and your y around, and then to get y by itself, you're going to raise both sides to the power with the reciprocal function, so 5 over 4, and that's fine. And so what we normally would do here is write something to the power of a fourth root, and what you get is a situation where, say for example, we were trying to find the number 4 to the power of 3 on 2. What we would do is write that 4 as 2 squared, something squared so that the 2's would cancel. But it could be 2 squared, it could also be negative 2 squared. And so that creates the situation where if we find the answer for this, we're going to have two answers, a positive answer and a negative answer. So that gives us a positive answer and a negative answer here as well. So that becomes an issue if we're asked to state the inverse of something where we've got a restricted domain for this particular function. So let me just sketch that section of the function. So it's the negative arm of that function. And so its inverse, when we reflect it across the line, y is equal to x, is still going to have that same kind of root shape coming this way, like this. So the function is going to be f minus 1, and its domain is positive reals, mapping to reals, and its formula is the fraction that we had, the reciprocal of the fraction that we had, 5 over 4. So here you can see the function that I was talking about, and I'm just going to flick on its inverse function. You can see that you get the positive arm of the inverse, so because it needs to be a function itself. And so the other arm for it goes, if I draw it in for you, actually comes down this way, like that. And you can see that that immediately fails the function test, fails the vertical line test. And so that's why I have it written here as a function, and that's why the calculator's not graphing the whole thing correctly for me. So you just need to be careful if you are graphing something that has a positive power and you have two arms of the graph that you get it correct. But let's just have a look at some of the other functions. So here is x to the power of 3 on 5, and there's its inverse function, x to the power of 5 on 3. Let's have a look at x to the power of 2 on 3, and again, of course, if I ask it for its inverse, I've only got half of the actual inverse as well, because again, we've got a 2, an even number, in our numerator. And the last thing to do for this exercise is to look at strictly increasing and strictly decreasing functions and the relationship between functions that are strictly increasing and their inverse and functions that are strictly decreasing and their inverse. But first of all, let's just look at the definitions of strictly increasing and strictly decreasing again. So if you have 2 points x and a where x is less than x and a and b where a is less than b, if the y value at a, so f of a, is less than the y value for b, what you have is a strictly increasing function across that interval. And that interval includes a and it includes b. If you have a situation where going from a to b this way, the graph is falling, then you have a strictly decreasing function. And again, the definition means that a and b are both included in the interval for strictly increasing or decreasing. So we include our endpoints. So when we're working with power functions and trig functions, we have some situations where we have increasing functions, like we have x to the power of 3. This is a strictly increasing function. Even though we've got a derivative that's equal to 0 here, the gradient doesn't actually define what is strictly increasing or strictly decreasing. Okay, so this function here is still increasing all the way along, so it's a strictly increasing function. Now, its inverse function, which is x to the power of a third, is also strictly increasing. Even though at the point x is equal to 0, the tangent is undefined, so dy dx is undefined, the tangent is vertical, it's still, if you have an a to one side and a b to the other, that interval from a to b along here is an increasing function, and so we have an increasing function. Now, in terms of defining strictly increasing and strictly decreasing sections for our trig graphs, we have that for this particular cos graph here, if we go from 0 to pi, we have a decreasing function. So our function is going down, and so strictly decreasing for 0 and pi. And we include our endpoints. So we started at 0 and we finished at pi. So across that domain there, the function is strictly decreasing. Now the weird part is, if we go to the other side and go from minus pi and come into 0, what we've got is an increasing function, and this value, the point at x is equal to 0, actually belongs to the section of the graph that is both strictly decreasing, so it includes 0, and strictly increasing, so it includes 0. So we don't define a particular point to have an increasing or be an increasing or a decreasing function. We're looking at the interval over which the function is increasing or decreasing, not at a specific point. We're looking at a section between 2 points. So let's look at some of the functions that we've looked at throughout this exercise and look at whether they're increasing or decreasing. So we've already looked at the cube and its inverse, the cube root function. So let's have a look at our other functions. So we've got our restricted cos graph and its inverse function. Both of those functions are strictly decreasing functions. For our restricted sine graph, strictly increasing, and its corresponding inverse also strictly increasing. And the same is true of our restricted tan function and its inverse tan function as well. So you can see we've got a pattern happening here, and I'll explain why it works. So you can see I've got a yellow function here and 2 points on that yellow function that are 2 across and 3 up to get from this one, 2 across and 3 up. So for its inverse function, if I reflect it across the line y is equal to x, what you get is this green function where to go from this point you go up 2 and across 3 to get up to this second point here. So in terms of whether the line is increasing or decreasing, you can see that there is still an increase. It's not so big an increase, but there's still an increase. And the same would work for a decreasing function as well.